Hello students, this is the 4th class of the lesson Electricity. I have made 4 videos on this lesson and this is the last part. Watch all these 4 videos to understand the lesson properly. Students, in today's class we are going to learn heating effect of electric current, Joule's law of heating, practical applications of heating effect and electric power. In the previous classes, we learned that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals and makes the electric current flow through a resistor or system of resistors. Also, we understood that to maintain the current, the source has to keep expending this energy. Then, where does this energy go? We often observe that electric gadgets become warm if used continuously for longer time. Why does it happen? Students, in any electric circuit, a part of the source energy may be consumed into useful work, like in rotating the plates of an electric fan. Rest of the energy may be expended in heat to raise the temperature of gadget. On the other hand, if the electric circuit is purely resistive, then the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Now, let's just recall and write the relation between the source energy, potential difference, charge, current, time, power and work done in an electric circuit. We know that potential difference V is equal to W by Q. So, we can write W is equal to VQ. In the earlier classes, you studied that rate of doing work is called power. So, power input by the source can be written as P is equal to W by T. We can substitute W is equal to VQ and write P is equal to VQ by T. Also we know that Q by T is equal to I. So we can write P is equal to VI. And energy supplied by the source in time T in an electric circuit is equal to work done in time T. We can also write it as rate of work done into time. You know that this rate of work done is power, so we can write P into T. Now, let's write this for a purely resistive circuit. When the circuit is purely resistive, what happens to the energy expended by the source? This energy gets dissipated in the resistor as heat. That is, in this circuit, the complete source energy will be expended to produce heat. Or we can say that the source energy is consumed and gets converted into heat energy. So, for a steady current I, the amount of heat H produced in time T is H is equal to PT. This is because, just see this slide. Here we have written energy is equal to P into T. And in this case, since all this energy is converted into heat, we can write it as heat energy H. So H is equal to PT. We know that P is equal to VI. So it can be written as H is equal to VIT. And also by Ohm's law, we know that V is equal to IR. If we substitute V is equal to IR here, we will get H is equal to I squared RT. This is known as Joule's law of heating. Joule's law of heating implies that heat produced in a resistor is directly proportional to the square of the electric current flowing through it. That is, H is proportional to I squared. And the heat is directly proportional to the resistance of the resistor, that is H is proportional to R. Also, the heat produced is directly proportional to the time for which the current flows through the resistor. H is proportional to T. Children, you know what is direct proportion? If amount of electric current is more, then more heat gets produced. And if current is less, then less heat. In the same manner, if the resistance is high, more heat. If the resistance is low, less heat. If electric current flows in the circuit for longer time, then heat produced will be more. If the current flows for a shorter time, the heat produced will be less. Now let's see the practical applications of heating effect of electric current. We know that heating effect is desirable in devices like electric heater, electric iron, electric bulb, electric fuse, etc. And heating effect is undesirable in devices like computers, TV, refrigerators, etc. Heating effect in electric bulb. In electric bulb, filament gets very hot and emits light. Most of the power consumed by the filament appears as heat and a small part of it is radiated in the form of light. Filament of electric bulb is made of tungsten because it has a very high melting point, which is equal to 3380 degrees Celsius, and so it does not melt readily at high temperature. The bulbs are filled with chemically inactive gases like nitrogen and argon to prolong the life of filament. Heating effect in electric fuse. Electric fuse is a safety device that protects our electrical appliances by stopping the flow of any unduly high electric current. It consists of a piece of wire made of a metal or an alloy of appropriate melting point. Fuse is always connected in series with live wire. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1 ampere, 2 ampere, 3 ampere, 5 ampere, 10 ampere, etc. So for an electric iron in which 4.54 ampere will flow in the circuit, a 5 ampere fuse must be used. That is slightly more than the circuit current. In this case, where 5 ampere fuse is used, the maximum current that can flow through it is only 5 ampere, and fuse will melt if the current through it exceeds 5 ampere. Electric power. We know that rate of doing work is power. That is, power is the work done in unit time. This is also the rate of consumption of energy. We can define electric power as the rate at which electric energy is dissipated or consumed in an electric circuit. The power P is given by P is equal to VI. By substituting V is equal to IR, we can write P is equal to I squared R. And by substituting I is equal to V by R, we can write P is equal to V squared R. The SI unit of electric power is watt. 1 watt can be written as 1 volt into 1 ampere. We can also write it like this. So 1 watt is defined as the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt hour. The unit of P is watt, the unit of T is hour, so it becomes watt hour. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. The unit watt is very small, therefore we use a much larger unit called kilowatt. You know 1 kilo is equal to 1000, so 1 kilowatt means 1000 watts. The commercial unit of electric energy is kilowatt hour, commonly known as unit. We can express this kilowatt hour or unit in joule. So 1 unit is equal to 1 kilowatt hour, that is kilo means 1000, watt, hour means 3600 second. We can write it as 3.6 into 10 to the power 6 watt second. So this watt second is nothing but joule. So 1 unit is equal to 3.6 into 10 to the power 6 joule. If you want to convert kilowatt hour to joule, then you have to multiply the same by 3.6 into 10 to the power 6 joule. Here is an example of how we calculate the energy consumption at our home. If one 60 watt bulb glows for 5 hours in a day, then for 1 month it will be PT. The power of the bulb is 60 watts and the time is 5 hours for 30 days. That is 5 into 30. So we will get 9000 watt hour, and if we convert this to kilowatt hour, it becomes 9 kilowatt hour or 9 units. Students, that's all in this lesson. Here are the questions. Check your understanding of today's class by answering these questions.
To watch more such videos, please subscribe my channel.